hit the record. Wonderful. So it's my absolute pleasure to welcome back Shantanu to our Astro Launch seminar series. I guess I'm welcoming him back, but I think it's the first time that he's with us virtually. So all the previous times, I think it was in person, if I remember correctly.
Yeah.
So Shantanu is an astrophysicist. Is just down the road from us at University of Western Ontario. Well, what used to be called University of Western Ontario, and now it's Western University. Shantanu did his PhD in '93, or finished his PhD in '93 at University of Illinois. He did a couple of postdocs at Michigan State and then at Canadian Institute for Theoretical Astrophysics, or CETA. And then since '99, he's been a professor at Western University. So Shantanu has worked on a variety of exciting topics in astrophysics, most of them around accretion disks, either accretion disks that form planets or accretion disks around supermassive black holes. And a lot of us, it's probably, you know, most of exciting astrophysics does happen in accretion disk in various places. So it's great that it's with us today. It's going to tell us about one of those exciting projects, in particular supermassive black holes in the direct collapse scenario. And that's about all I have. So take it away, Shantanu.
Okay, thank you, Niayesh, and thank you to everyone. Thanks for inviting me. It's a pleasure to join you all, even if virtually. And I look forward to, you know, I think even going forward, maybe we can make more use of this kind of interaction, even in addition to regular visits. So I work primarily in star formation, but today I'm talking about supermassive black holes, something some of you may know a lot more about than I do. But it's obviously a very interesting field with lots of new information, and we found it's a very nice area for adventurous theorists to get involved in. So I'm very grateful to my collaborators. Yes.
Can I ask you something? Do you mind being interrupted or to answer questions during the talk?
It's up to you. Yeah, it's fine. I mean, if it's going too long, then I might, you know, give short answers and come back to it later. Yeah, so that's fine. And actually, I've kind of made my talk approximately half an hour, maybe slightly more, because I feel online talks should not be too long. So, and in fact, I'm going to present. So interruptions will be fine. I think we'll be well within an hour. And I'm giving essentially two talks. One on our work on the mass function of the supermassive black holes in the DCBH, or direct collapse scenario, and the other one is actual simulations of the formation process, including magnetic fields, which I love to do. So let me first of all thank my collaborators in these endeavors, who are Arpan Das, who is a former PhD student of mine who defended last year and is now doing research at NASA Ames Observatory, and Shingo Hirano, who is a postdoctoral fellow at University of Tokyo, and Masahiro Mashida, who is a professor at Kyushu University. So supermassive black holes, as you will know, have now been observed at redshifts as high as about 7, which is approximately 700 million years after the Big Bang. But the most massive of these black holes are at least 10 to the 9 solar masses, in one case even about 10 to the 10. And you can see from this figure from Banados et al. That if you plot the most massive, let's say you take the 3 most massive black holes observed, the dark blue, the black, and the red, as well as the several others plotted, and you run the clock backward. That is, you assume that they were accreting at the Eddington limited accretion rate, which is, as we'll see later, an exponential growth rate, and you run the exponential growth of Eddington accretion backward in time to approximately the redshift where we think the conditions were even right to have gravitational collapse, so around redshift 20, let's say, then running the clock backward would mean that the progenitor was around several times 10 to the 4 solar masses, so not stellar mass black hole territory. And so that's the basic problem, that if you have to create billion or even 10 billion solar mass objects at about 700 mega years, you need initial seeds to be massive, very massive. And the one of the more promising mechanisms to start with such.
So Shantanu, can I ask you a question just about that? So one of the kind of problems I've had with this plot is that this does depend very much on the spin that you're assuming for the black hole. So, and I mean, if it's highly spinning, then this is the problem. But then if it's not, then if it's not a spinning, then it would be, I mean, you could start with a smaller mass. So, I mean, what spin do you assume here?
Here in the initial work, we're not taking any, really not addressing that. In the second work, we will actually have simulations, and the spin is relatively low because we have magnetic braking going on. So that's one mechanism one can argue to start off with low spin rates.
Right, but I'm saying that plot you were showing that you're accreting at Eddington rate in the previous slide, right?
Yes.
So because the Eddington rate is the luminosity, but how much mass is increasing, that depends on the efficiency, which depends on a spin. So
right.
So I think one of the at least my criticism of this argument is that it actually depends on the spin that you're assuming, and I think there could be a big problem or not a big problem depending on basically what the spin is.
Okay, fair enough. Yeah, you're saying that, yeah, because of the disk-like accretion, you might, the mass accretion rate, and you could have Eddington luminosity, but not Eddington mass accretion rate, right?
Exactly.
Yeah. Okay. Yeah, fair enough. Anyway,
doesn't the spin just make it worse? I mean, the spin just makes the problem worse, right?
Yeah, I think for bigger spin, it's a big problem, but I think for a smaller
that's right.
spin,
So this is the minimum problem right here, right? So it has to be at least 10 to the 4. So that seems like a reasonable start.
The spin can work in the opposite direction too. Yes, in the sense of the angular momentum barrier, which again I'll talk about.
Well, so we can come back to this, but I mean, I think his problem is sometimes overstated, which fair
enough. Yeah, it's definitely a very back of the envelope estimate, and in fact, it's on the next slide after this one. So let me get through this slide, and then we have another plot which kind of shows the back of the envelope argument. So the DCBH idea is that if you could eliminate the primary coolant, which is molecular hydrogen at this stage, through Lyman-Werner ultraviolet radiation. Now you need that radiation to come from some first generation of star. But if you could eliminate the H2 content in some halos, then the gas would maintain itself at about 10,000 Kelvin. And at that temperature, not only is the Jeans mass quite high, it could be 10 to the 5 solar masses or so, but the accretion rate that you would estimate, again, back of the envelope accretion rate is always the sound speed cubed divided by gravitational constant. And that would be of order, close to 1 solar mass per year. And at that rate, you are essentially preventing the star from undergoing its Kelvin-Helmholtz contraction and reaching very high temperatures, which I'll talk about later, actually. So in fact, I'll defer that because that's on a later slide. But you need the high accretion rate to keep the star growing without the radiative feedback. In any case, once you get up to 10 to the 5 solar masses, these objects could collapse. They could essentially implode. And again, I'll talk about that later. So this is a way to create one direct collapse black hole. If you create one halo with no molecular hydrogen by dissociating it. But then an idea that's been pushed a lot in semi-analytic modeling has been that this could lead to a chain reaction, that the supermassive star or supermassive black hole actually, once it forms, would put out more Lyman-Werner photons, and that would create more molecular hydrogen-free halos in its neighborhood. And so you can imagine it's a chain reaction. And so the simplest way we understand chain reactions is that you get an exponential growth. of the numbers of these objects until you go too far and something shuts it all down. So the positive feedback in this DCBH idea is that each DCBH contributes more Lyman-Werner photons, which then creates more conditions for DCBH formation in surrounding halos. On the other hand, the expanding universe, the metal enrichment that will be happening due to star formation will work against this. And finally, if you have too many of these supermassive black holes, excuse me, they themselves may give enough radiative feedback to photoevaporate the host halos. So we're looking at this from a basic, simple theorist point of view, outsider theorist, let's say. So if you have a chain reaction and you have exponential growth of numbers, and each black hole is also accreting at the Eddington rate, which is also at least approximately exponential, then you can explain some very basic features of the observed luminosity function. That's what the bottom line in this part of the talk. Here's just a primer on the back of the envelope calculations that Niesh was referring to. So basically the idea, again, if you look at this cartoon, if you run the clock backward from observed quasars, you can get to masses, whether you call it 10 to the 5, 6, or 4, something very massive if you're going the Eddington limited accretion route. But if you start with stellar remnants, even assuming they're as high as 100 solar masses, you have to account for the fact that the photoevaporation due to the surrounding H2 regions and so on would actually starve the stellar remnant initially of additional accretion. It might pick up at a later time due to some gas inflow, but at that point, you have to really climb a very hyper-Eddington track to get to the observed mass. So this is the back of the envelope calculation. If you do have Eddington limited growth with a standoff between the radiation pressure on electrons versus the gravity of the protons, you can show that you get this very nice exponential growth in which the growth time depends essentially on the Salpeter time, which is all fundamental constants. And then you have a correction factor, which is approximately 0.1 due to radiative inefficiency. And then you could stick in an Eddington factor in front too, which normally will just take to be 1, but you can let it be slightly more or less than 1, assuming you have somewhat super or sub-Eddington accretion. So the usual practice when you fit the luminosity function of quasars, and this is the data points here are redshift 3, although higher redshift is also available, but at redshift 3 you have a significant number of data points. So the usual practice of Hopkins et al. And many others is to fit the data with a double parallel. So that's been going on for many years, and that's all very nice. You can draw a straight line here and a straight line there, but that doesn't give you any insight into why the distribution has that form. So what we tried to contribute is a explanatory model based on very simple assumptions, which I've already stated about exponential growth in number, as well as exponential growth of the masses. And so bottom line, the red line here is our model best fit with the best fit parameters. And this does, mathematically, as with a job as fitting 2 straight lines, maybe better, but it gives you the insight that, okay, I can actually interpret the slope of the parallel in terms of something about the formation. And I can also interpret the turn down in terms of something physical. Okay, so as I said, we just need a few ingredients in this recipe. You add your dash of salt, dash of pepper, and take your base. So we really have these 3 assumptions. First of all, that you start the DCBH with a set of seeds of 10 to the 5 solar masses. We take a log normal distribution. And then the 2 assumptions that I've stated already, that the number density is growing exponentially due to some kind of chain reaction process, but it does shut off at some time, which we call capital T. So T0 here is whatever time the first DCBH is formed. You might think it's around redshift 20, and then capital T is the time later when the whole thing stops. And then each object is growing at either the Eddington rate, or you can set that chi factor to be not equal to 1. It'll still be exponential, but a little bit super or sub Eddington rate. So here I'm going to go through very quickly. You don't really like to have equations, but basically here you see a log normal distribution. If you set time equals 0, it is a log normal. If you have finite time, if every object grows exponentially, then ln m just changes by factor gamma t, so you just have a shifted log normal. But if the times of growth are not the same for every object, if you have a distribution of times of growth, f of t, then your final distribution is this convolved integral of the log normal and that distribution of time. So no need to go into the details. If you assume exponential growth of numbers, then this is the f of t that will go in the previous integral. Again, capital T is when the whole thing is finally halted. And in that case, again, just skipping all of the math, we can see visually that if you start with this brown dashed line, which is a log normal distribution peaked at around 10 to the 5 solar masses, and you let this kind of process continue, these are the same function with different parameters. This is the nasty function here. You can ignore all the details, but you can see that there's a power law lurking in there somewhere. And then there's terms that truncate it at two ends. And you'll basically develop a power law. And if the capital T goes to infinity, the power law goes on forever. But if you cut off the growth at some time, then the power law won't grow indefinitely and you'll have a turn down. And so despite what looks like nastiness here, really it's very simple interpretation in terms of parameters. You have a power law tail whose index is just a dimensionless ratio of the two important timescales or rates. The lambda is the growth rate of the numbers of DCBH during that duration. The gamma is the growth rate of the mass of the DCBHs. The beta, which is another ratio of timescales, essentially this is the ratio of the total time divided by the number of mass, so it's the number of mass growth times. It's the total time divided by the mass growth time. And that beta parameter tells you where the trend down happens. So now, again, here's the Hopkins data. Again, alpha is this dimensionless number, beta is the other dimensionless ratio of times. And to go from mass to luminosity, we've made the assumption that the luminosity is proportional to mass. That is, it's something to do with the Eddington rate. And we get reasonable fit with these parameters. Okay, but what does that mean? What does alpha of a half mean and beta of 8 actually mean? Well, the good news is it's better than fitting the double power law. If you fit straight line here and straight line there, you would have no interpretation of what those slopes actually meant. In this case, you can convert these dimensionless numbers into dimensional numbers, and you get numbers that make sense. That is, your fit is not wildly out of tune with estimates that are made based on cosmological models and semi-analytic models. So you basically get these parameters if you have a duration of about 150 megayears. So let's say somewhere from 200 to 350 megayears after Big Bang. The population growth rate, the number density growth rate, is actually more or less what Dijkstra et al. Estimated from a semi-analytic modeling of this exponential growth rate. And the chi value, the super Eddington, is about 3. So, you're in the territory of mildly super Eddington. So again, it's not something crazy. It's not 100 times Eddington. So with approximately Eddington, with about the right amount of time, with the estimated growth rate of numbers that others have estimated, you get something that that fits the data approximately and gives you an idea that, okay, this is telling me about the growth rates, and this is telling me about when the growth stopped. Okay, so this is really the last slide on this topic. and again, this just reiterates the points that using this model, we can interpret the power law slope, I would say for the first time, as a dimensionless ratio of two important growth rates. And we can also interpret the breakpoint as telling us something about when that growth era ended. So if you assume there was a short period of exponential growth, you can understand the power law and the tapering. Okay, so that's the end of this part. And of course, it's a minimum hypothesis model. And there's obviously so this is happening roughly between redshift 20 and 13. And then the mass function would stay frozen if there was no further accretion, but we know there is further accretion. If that accretion was at some sub-Eddington rate, but still proportional to Eddington, the distribution would shift a little bit to the right to higher masses. But mergers can also be happening, as we know, and that may also affect. So these are next order evolutionary components that are not in our model. And for that, you have to go back and really parse the data for redshift 3, 4, 5, 6, where you have enough statistics and see if there's a trend that you can identify and actually model. But that change is not so dramatic compared to the formation process itself and its effect. Okay, so now I'm going to move on to physical modeling of the collapse process itself. And yes, angular momentum, as Niesh brought out, is a big bugaboo. You worry about it a lot because the idea of direct collapse is that you have high temperature and therefore rapid collapse. But we know that collapse just doesn't happen spherically. There's always angular momentum, and so you're going to form a disk. And if you form a disk, all bets are off, right? The disk can fragment, you can get multiple objects. It's not clear that all that mass would end up in a central object that we call the supermassive star, which would then collapse to form a supermassive black hole. So with Shingo Hirano and Masahiro Mashida, we did these three-dimensional simulations to see if the magnetic field could be helpful. Now, we know from present-day star formation that magnetic braking is at certain times very efficient at removing angular momentum, but we also know that that disks do form, and you don't get supermassive stars in present-day star formation. In fact, in our field, there is this thing known as magnetic braking catastrophe, where if you use ideal MHD, you actually cannot form a disk in a simulation. So we need non-ideal MHD to understand why disks actually form, and that's not a problem. We expect in partially ionized gas that there will be a lot of non-ideal MHD effects. So if we look at it from, again, theorists' point of view, there's really four limits of magnetized collapse. You can either have negligible magnetic field where the mass to flux ratio, this is the normalized mass to flux ratio. It's essentially a measure of magnetic energy to gravitational energy. If this number is much larger than 1, then mass dominates the magnetic field, gravity dominates, and so it's like there's almost no magnetic field. But if you have ideal MHD, then the field is still dragged along. On the other hand, you could have weak magnetic field and non-ideal MHD, but then the magnetic field could be very strong. You could start out with approximately critical magnetic field, or even you could have mu could even be slightly less than 1. You can have ideal MHD, and then you can have non-ideal. So in our present-day star formation simulations, we're in this bottom right limit. We have strong initial magnetic fields, but we must take into account the non-ideal MHD due to the partial ionization. Turns out in the high redshift limit, you can actually go to ideal MHD up to much higher densities than we do in present day. And the magnetic field actually is not very well constrained. We don't have any measurements, so we rely on theory. And so there are constraints you can put on magnetic field, I think from even CMB, and those, imply, that field couldn't be above some limit. But no matter how you parse it, every estimate anyone's ever made, the field is very weak at these high redshift stages when you measure it according to mass to flux ratio. So we're going to be working in that top left limit in the simulations that I show you today. Okay, right. So we're starting with a Bonner-Ebert sphere, but the initial temperature is that which is characteristic of atomic cooling. So it's almost 10,000 degrees Kelvin. We have a background magnetic field that's very weak. We picked this 10 to the minus 12 Gauss at 10 to the 4 density based on cosmological simulations. Those cosmological simulations are often assuming some growth of the magnetic field by the Biermann battery process, which I can talk about later if you want to know. But that is a process that's not some exotic, early universe inflationary scenario for magnetic field, but something that might happen during the galaxy formation stage. And it's a way to essentially create magnetic field without having a pre-existing magnetic field. There is actually this one mechanism, Biermann battery, in normal plasma physics. So if you start with these kind of conditions, and we start with a very low rotation to gravitational energy ratio, which again from cosmological simulations and also present day simulation, we almost always see that on the large scale rotational energy is negligible. But again, notice that under these conditions, this temperature, our Bonner-Ebert mass is about 1 million solar masses, and the radius is about 10 parsecs, not more like 1/10 of a parsec in present day star formation. So if you follow the temperature curve for primordial gas, okay, so this is almost zero metallicity. It's effectively zero metallicity, and in that case, you kind of have a quasi-isothermal collapse until you get to about 10 to the 16 particles per cubic centimeter, at which point we make the equation of state very stiff. So that's the solid line, and the actual calculation may be more like the dashed line. So in order to prevent things from collapsing further and killing the simulation with tiny time steps, we have a stiff equation of state at 10 to the 16. And all the estimates are that up to 10 to the 16, the evolutionary time should be shorter significantly than for example, the ambipolar diffusion time. So we are reasonably confident to stay in the ideal MHD limit. Okay, so we've got that stiff equation of state, and we then, when a region gets to that density, we consider it to be a protostar. So you'll see that in the later images and animation, that these dots are really the regions that have reached that high density. So we're using a nested grid code. There's about 18 levels of nesting by the end of the simulation. So you're starting at a cell size might be a parsec on the very coarse outer scale, but down to about 1 or 2 astronomical units on the smallest scale. Okay, so here is a series of evolutionary snapshots in a time after a central protostar is formed. So you've got a central protostar that's reached 10 to the 16 per cubic centimeter. The top panel shows the mass histogram of the protostar fragments, because you've not only got a central object that you do at t equals 0, there's no histogram, but at later times you have other protostar objects as well, and eventually you have quite a lot. The middle panel are the density maps in the equatorial plane. Again, you started with rotation perpendicular to equatorial plane. Magnetic field is also in that direction. The bottom panels are the magnetic field strength at the various times. So the key result is that after this protostar forms, which is what we call the accretion phase, the rapid rotation in the vicinity of the protostar leads to a small-scale dynamo. And this leads to an expanding region of strong magnetic field. Remember, magnetic field was very weak initially, dynamically. It's been enhanced by gravitational collapse and flux freezing, but now it's also further enhanced by a dynamo effect. This enhanced magnetic field and the dynamo is actually very much aided by the formation of these fragments and all the nasty, excursions that they make. The field then, the enhanced magnetic field, enhances the collapse by removing angular momentum through magnetic braking. So the rotation leads to magnetic field, more magnetic field. The magnetic field then removes more angular momentum and allows more mass to come to the center. Okay, so let's play an animation. We have number density, magnetic field, and plasma beta, which is this ratio of gas to magnetic pressure. Notice the formation of many protostars and the expanding region of the magnetic field in orange and yellow. The plasma beta is inversely proportional to the magnetic field and becomes smaller, therefore more purple in the same regions. The magnetic field also enhances the coalescence of the fragments by removing their angular momentum. So this is an important effect again. By removing the angular momentum of the fragments, it allows the fragments to merge with the central protostar. See, I'm big for time. Okay, I'm good. I'll let this run. Okay, so let it run quickly while I say a few more words. Maybe advance it. Okay, so it's true that you get many fragments forming, but it's also true that the fragments enhance the magnetic field, but then the magnetic field helps these fragments to coalesce to the center. So the magnetic field is enhancing the mass that can go into the center, and therefore enabling the formation of a supermassive star. So if we focus on the mass growth of the central fragment plotted here.
Can I just ask you a question, Shantanu?
Please.
Those simulations you just showed looked very symmetric. There's a four-arm spiral there. It looked very identical, all four arms, but it very quickly broke into not axisymmetric. And I was curious about that. It's just that you put some random enough, it's like it's chaotic. It grows so fast into something else.
Yeah, my experience with doing a lot of these kind of simulations, even with the non-magnetic simulations, is there's always enough perturbations in your simulation to break these symmetries. I mean, it may even just come from your potential solver. You're going to get something that's going to break any beautiful, two-arm spiral or even four-armed. Yeah, so I think those are. If you had a two-arm or four-arm, it's probably not energetically favorable anyway compared to one-armed. Yeah, so that's the best I can tell you. I think the simulation naturally creates this complexity.
But very quickly.
Yes, a lot happens very quickly actually in this simulation. Now, we've only gone to less than 1,000 years past the protostar formation. And it's actually, even within the first, 10 to 100 years that you get very significant complexity. And that's when the dynamo actually works and generates a very strong magnetic field. So yes, things do happen very quickly. The dynamical time is, of course, very short near the protostar. But I'd say it was a surprise to us that the dynamo action happens so quickly and so effectively. Okay, so here we're just comparing the standard magnetic field model in red, where the solid line is the total mass in all the fragments, and the dashed line is the mass in the primary. And you can see for the most part, the primary dominates. It has almost all of the total mass at most times. The gray model is a model with no magnetic field. So even with no magnetic field, you have some growth of the primary. There's going to be gravitation. The non-active symmetry is going to lead to torques, and you will have some fragments coalescing to the center and some direct accretion. But you can see at some point, the magnetically induced accretion really takes off and is much more rapid than the non-magnetic. And I don't have the plots with you. We can check our paper. We even have models with other magnetic field strengths. So if you have a stronger field, it's even a more sharper upturn. So that is the bottom line here, that you're getting a very rapid growth of the central object. So even within 1,000 years, you've grown to almost 10 to the 5 solar masses. 10 to the 5 solar mass is kind of a special mass, as we're going to talk about. Now, in this case, we have stiff equation of state. So everything that's going into that central protostar is kind of being held there by the stiff equation of state. We're not following the detailed physics of what would be happening inside the protostar. But we have to stop for many reasons. One is the time step becomes too short at this phase, about 100th of a year. And that even is, that short time step is actually not necessarily even because of the central collapse. It can be because of the very low density magnetized envelope where the alphane speed is very high and you need a short time step.
So can I ask something?
Please.
What's the explanation, if any, for those fluctuations in the red curve? So the primary has almost all the mass, and then it loses some, and then it gains some, and then it loses some at late times. Like what's that about?
Mm-hmm. Yeah. I think the decrease may have, honestly, I can't give you an exact answer, but I think it may have a lot to do with how we're measuring the mass itself, right? Because you're always measuring it in some region. And so whenever we have those short-term downturns, it may just be how you measured it. You picked a radius within which you're measuring the mass, right? So I would attribute it to that. That is a solid line. It does a slight decrease. As far as the dashed line.
Yeah, I meant the dashed line.
Okay, right. I'd have to think about that. Okay, to be honest, it's happening at two particular times. It may just be that at that time, there's been there's a lot of fragments forming, and then they're going to coalesce again. So there may be some episodes of fragment formation. Perhaps that's in the movie, but that's really interesting. Yeah. So I don't know. Anyway, that's something I'll look into. Yeah, I can get back to you, but I think it has to do with the stochasticity of the fragment formation. So what's happening inside that central protostar? Okay, we're not modeling the detailed physics, but basically it's going to stay in this rather expanded state with a low surface temperature of just thousands of degrees, as long as the accretion rate is high enough that you can bring the energy in and you're not losing it fast enough, and the star expands, it gets bloated. And so unlike normal massive star formation, where your massive protostar gets very hot, nuclear reactions may even start, and you start ionizing radiation feedback that can limit the further growth. In this case, if you're feeding feed the baby fast enough, it's just going to keep growing. And if it's growing, it's cooler, it doesn't give you the radiative feedback. So in the normal POP3 scenario, work by Hasakawa and collaborators have shown that the radiative feedback can stop the formation as early as 40 solar masses. But if you can get the accretion rate high enough by having a very high temperature progenitor cloud, again, this is why I need to eliminate the molecular hydrogen as a coolant, then you could keep growing. And at that point, the star just keeps growing and growing until it gets to about 10 to the 5 solar masses. So that point, you have the general relativistic counterpart of, say, critical Bonner-Ebert mass. At some point, you just can't hold the thing up. There's too much gravity. And of course, as you know, in GR, high pressure means even more gravity, which is not the case classically. So at some point, you are going to hit the limit, and you have no choice but to collapse. So that's estimated to be about 10 to the 5 solar masses. And that's why we start our DCBH seeds in the previous model with that, mean mass. Okay, so that's what you expect will happen. So in the simulation, in 1,000 years, we've gotten close to the 10 to the 5 solar masses. And so again, we're proposing that because you're in this regime of nearly ideal MHD with a weak magnetic field, you can actually get most of the mass to fall into the central object, which is not something you could do in the present day star formation scenario. Okay, so this is the last slide for just the magnetic field part. So as I just said, we're saying that the magnetic field is very important in getting mass to the center. It's aided by the small scale dynamo, which itself is enhanced by the formation of the many fragments and the way they drag the magnetic field around. So when you can extract angular momentum from the accreting gas and from the fragments, you get more coalescence to the center. And so I think there's a more viable pathway to the DCBH scenario than one would have in the absence of magnetic fields. So for example, even if you had some molecular hydrogen in the halo, perhaps near the center, right, where you have the most shielding, it's possible that the overall collapse could get started because you still have something that's roughly, Jean's mass at 10 to the 4 Kelvin. And yes, you may have molecular hydrogen cooling in the center, and you may get a lot of fragments, but you may also have a lot of magnetic braking that could, it's one thing to get a lot of fragments, but then if they all fall to the center, you still get a massive object. So I'm speculating about something we've not done in that case, right? We've done the case which is all pristine gas, but I think magnetic fields hold some hope now that you can maybe get DCBH formation, even if you don't have the perfect fine tuning of exactly no molecular hydrogen. Okay, so on that speculative note, I will end. Happy to take questions. Thanks.
Thank you very much. I can audibly or virtually, whichever you prefer. Wonderful. That's very nice. Both topics. So any questions, please feel free to raise your hand for Shantanu. Just gonna wait. So can you repeat what your speculative note was? Because I think I got lost for a second there.
Yeah, sure. Yeah, well, so in this DCBH scenario, the normal idea is you need enough Lyman-Werner flux to dissociate all the molecular hydrogen. And then people argue about how much flux do you actually need? What's the critical amount of UV flux to actually dissociate all the molecular hydrogen in a halo? And people have different estimates. So if you need only a little bit, okay, maybe you could get rid of molecular hydrogen in lots of halos. But if the critical threshold is very high, then maybe the process is not so efficient, and one DCBH creating another pristine halo and so on. So for this whole thing to take off and have this exponential growth of DCBH, you need it to be very easy to eliminate the molecular hydrogen in neighboring halos. So what I'm suggesting is maybe even if you couldn't eliminate it all, if you could eliminate 80% of it or 90% of it or something, you don't have to do all that last bit, because even with some fragmentation due to molecular hydrogen, you may still be able to coalesce into a large primary.
Okay, I see. So this real question is how much molecular hydrogen you can or you need to get rid of, and I guess you're saying there's some uncertainty there. Yeah. Okay. Other questions?
I don't know how to put my hand up. Can I ask a question?
This works. There you go.
Very nice talk, Shantanu. I have so can we circle back to Niyesh's initial question about spin? So I gather the magnetic braking removes angular momentum, so you end up with this big progenitor that is presumably slowly spinning. And then, so, how do you then spin these? I mean, clearly it still needs to accrete many, many, many times its current mass. So why won't that process of growing the black hole to 10 to the 9 then, if it's similar to this, why do we end up with rapidly spinning black holes? Depending on whether it's, accretion by gas coming in or, I'll just leave that to you. I can think of answers, but I'll let you comment on that.
Okay. Well, you probably better than me, actually. I mean, that whole phase of what happens after you have this 10 to the 5 solar mass DCBH, you still need to provide the 10 to the 9 solar masses of gas from somewhere, right? That wouldn't be in the original reservoir necessarily at all. So that has to come from somewhere, and that may be where you're gaining the angular momentum. But for the phase we're modeling, the inflowing gas into the protostar is very subcaplarian. It's about 1/10 of capillarian because you have torqued down the gas. So having a slowly rotating supermassive star is actually helpful in the sense of allowing the instability to occur and the object to collapse at about 10 to the 5, sort of with our expectations. If you had a very rapidly rotating supermassive star, then the criteria are different, right? It could maybe get to much higher masses. So we're happy to form this slowly spinning supermassive star and then say it'll collapse at 10 to the 5, which is the right estimate for the progenitor if they then grow at Eddington rate to get to 10 to the 9. But yeah, why that final 10 to the 9, 10 to the 10 solar mass object has a rapid spin, I can't say. I haven't really thought much about that part of the growth process.
Okay, so the difference between your scenario, I'm just trying to place it in the context of the history of this thing, is the quasi-stars that were proposed by, I don't know, Beagleman and others years ago. The big difference now is that you've added magnetic fields to it, which have a big positive impact on the stability and the ability of these things to accrete. Is that accurate? Is that the primary difference in the scenario, or?
Yeah, I mean, I'd say we're adding this to the supermassive star scenario, and I'm trying to remember that I think there are some subtle differences between the quasi-star that Begelman proposed.
Yeah, you end up with a black hole, almost as a black hole nucleus, which then continues to accrete. So the black hole grows from the inside out. It's not clear if that's happening here. Is that what's happening here? You got a black hole growing from the inside out?
Well, I think what's happening here is, you get your 10 to the 5 solar masses packed into a supermassive star, and then the star implodes.
Okay, so it's a fast implosion. Is that the idea?
Yes.
So does that have observational signatures that might be
yes,
approachable from, say,
right.
Webb or other?
Right. I think that's a key target. Absolutely. That's a very exciting possibility. Probably if these things are at redshift 13, they're probably still too faint. But if it's redshift as late as 10, 9, then they might be bright enough to be seen by Webb. So most estimates for Webb are a little bit pessimistic that you can see these objects because of the purported redshift that they would be at, let's say around redshift 13 or more. So another thing that one could do is try and look for them through LISA in the future. If the supermassive star collapse is not spherically symmetric. So in this case, there is some rotation. You go back to that case, there's some rotation. In that sense, people have done calculations. I think Shapiro and others have done calculations of the kind of the rotating collapse. And there, I think the general consensus, is that with LISA, you should be able to see some signal from those very high redshifts.
So I'm sorry to hold you here, but this is really interesting. So how much of the, do you have an estimate of how much mass would be lost during the collapse? Does it all go down, or is it essentially like a supernova where a significant fraction of the mass is lost in the implosion?
Mm-hmm.
Is there a bounce?
Yeah, someone else may know more than me, but my feeling is most of it does go in, but there's also, if you look in detail, the whole theory of the supermassive stars, there is a certain mass range where you could get a supernova. So there's some regime where you get a supernova, but for most of the regime, you just get implosion. Again, someone may know more than me, but that's my understanding. And we usually overlook that supernova possibility. It's true.
Okay.
So Rob has his hands up.
Yeah, that's right. Brian stole a lot of my questions, but anyway,
Sorry,
so
Rob.
related to that, I'll ask them naively. You might have said, so 10 to the 5, is that good enough to get all the supermassive black holes that we observe now, or does more have to happen? That's one question. It's partly related to the mass loss, but naively, is that good enough?
Well, I think it's good enough to get you, if you're accreting at Eddington rate, in about 500 million years, you'd accrete about by a factor of 10 to the 4. So if you form these things at 200 million years and you've got 10 to the 5 already, then you can get to 10 to the 9, by 700 million years after the Big Bang. So it is sufficient with these masses to get to those very high mass black holes. Of course, we don't really know how many of them there really are. There are just a few that's observed, right? So the actual number density in co-moving frame is really hard to still pin down. So there is also the question as to whether you can explain the entire population of supermassive black holes of all masses using the DCBH scenario. So that's an interesting open question.
That's kind of what I was wondering. So let me ask something else, maybe very naive. What about, when you had these simulations, you're forming a heavy thing in the middle, but a whole bunch of other things. So why can't, instead of just, accreting matter or imploding, why can't this thing start gobbling up other protostars or black holes and get bigger that way? Or is that just not efficient enough?
Well, it depends what's in the surroundings, right? It's true, and this, even after it forms in this way, if it is going to be part of some galaxy, right? And there will be other mass available. And again, that's presumably how you get to 10 to the 9 or to the higher mass.
But maybe it isn't all Eddington. Maybe it just starts eating things or colliding with things and getting bigger.
Right.
And I have no idea if that is better than Eddington or worse than Eddington or what. That's my question.
Right. Okay. I think that some estimates by Loeb and Pacucci have estimated that, after in more recent redshifts, if that's the right word, then the mergers are playing a bigger role than accretion. And so to fully understand the mass function and luminosity function, I think one does have to account for the role of mergers in addition to ongoing accretion that occur during the galaxy hosted phase. And I think that's where, I have a slide here. So here's a paper from Kulkarni et al., which is too hard to read all the details, but this is, you've got redshift bins of up to 0.4, up to a half here, about 0.7, about 1, about 1.1 or 2. So, and then it goes down. This is redshift 2, 3, 3.5, 6. And you can see the statistics are less as you go to higher redshift, as you go down. But so there is some evolution going on here. And I think that is a very interesting thing to further model. Our modeling kind of assumes that you're frozen in place with the basic picture at high redshift, but subsequent evolution doesn't do a lot. And you can see that you pretty much have this, I'll call it double power law, that's what they were fitting. You do maintain a double power law, but there is some trend in the best fit parameters. And there is some weak growth of masses, but not a lot. So there is probably some limit to how much mass or luminosity you can get. That's an outstanding thing to fully model the subsequent evolution, which can be and is claimed to be dominated by mergers rather than accretion. And then the other part of your question, I think about the total number density, I think is an interesting question too. Like, are you freezing in the current, you can estimate the number of SMBH per co-moving megaparsec cubed in the present day universe, right? I forget the number, 10 to the minus 2 or something like that. And then you can ask, is that fully accounted for by this kind of modeling, or do you need the subsequent formation of SMBH in galaxies to get the total number density? And I can't answer that. I mean, we actually have not, we're fitting the shape rather than the absolute number in this model, because your number density went as some, exponential, but we didn't fit the actual number.
Okay.
Yeah.
All right, thanks. That's a good, interesting talk. Thank you.
Thank you very much, Bob.
Other questions for Shantanu? So let me just circle back just as a final question, since I don't see anyone else, to what I was pointing out early on. So there's this thing about, I think you did show it in your third slide, then this efficiency that you assumed is 0.1, which in fact, I mean, ranges from 5% to 30% roughly, depending on the spin, right?
Right.
And remember that actually goes into the exponent. So you're changing you can change your exponent by a factor of 6. So that could actually have a dramatic effect on the mass, on the final mass, because you're looking at the exponential of that times the time. So the analysis that we did a few years ago, and we were wondering about basically the cosmological implication, that maybe you need a cosmological fix for this. The analysis we did is that the main uncertainty is in fact there, because that's where if you change the efficiency by a factor of 6 and that goes into the exponential, that could change the final mass by quite a lot, or the required initial mass. And I was just looking back at our paper and was saying that if you have a spins of either 0.3 or 0.4, then that's enough to basically start from like a stellar mass object. If you had spins that are much smaller, then you're actually okay. If you had spins that are bigger than 0.3 or 0.4, then there is a problem, and you need much bigger progenitors, basically, like what you have. And I think probably, a spin of now. Then the question is, at this Eddington accretion, at what spin do you think most of it is happening? And I think I don't actually know the answer to that, but I think that would be the main uncertainty in this kind of analysis, because again, since it is in the exponent and it could change into by a factor of 6, then really if the spin stays small or stays big, that could make a big difference, right?
Right. Yeah, that's a good point. Yeah, well, definitely. So the Eddington factor you're saying can be as high as 0.3 or 0.4?
The spin, sorry, what we were finding is that if the spin is around 0.4, then it has the right efficiency to
The
give you
efficiency,
basically that, yeah, you get
Mhm.
gets the right efficiency to get the black holes we see at right now, basically at redshift 6.
Mhm.
If
Okay.
spins are lower than that, then you're okay. If spins were higher than that, then you have a problem basically, and you need much
Mhm.
bigger progenitors basically. But I think the thing that wasn't clear to me before that analysis was, I mean, the role that a spin could play in all of this, because I think usually people don't talk much about it, because I've heard a lot of talks about this, but nobody had mentioned this, that in fact, this spin evolution, which as far as I understand, is very uncertain throughout the whole process, is could make a big difference in what comes out at the end.
Mhm.
So yeah. Okay, so I think
Yeah,
we are
fair
at
enough.
12:30. Yeah, and I think we should I think we can continue talking about this later. But I think it was very excellent talk. Thank you very much, Shantanu, for making the time for us. I don't see any other last minute questions. So let's thank Shantanu again. And hopefully next time we can actually have you in person.
Yeah, I look forward to that. Yeah, definitely. Yeah. Good time's almost here, I hope.
It's almost there until it's not, and then
Right.
yeah, but
Yeah,
very
yeah,
close.
exactly. One more wave. Anyway, very nice to be in touch with you all. I really appreciate it. And yeah, it was a great session. Thank you. So look forward to next time.